Continue. All right, so yesterday, oops, I got the microphone actually on. Yesterday we had a few takeaways, some important things just to kind of recap. So we had, sorry, it's a little loud. We had the idea that the center of the nucleus, or the center of the atom, that nucleus, is going to be where almost all of the mass of the entire atom is found, right? And then we have, what's between the nucleus and like the rest of the atom? What was that? Yeah, like empty space. There's not a whole lot going on in there at all. And so that funny little video of the guy floating around and he's like, it's just empty space, right? And then you have the electrons kind of floating around out there. So you have that kind of idea. So most of the mass is right there in the nucleus. What is in the nucleus? What subatomic particles? What are the two that are found in there? What's in the nucleus?
Protons and neutrons.
Very nice. And then what charge do the protons have again?
Positive.
What charge do the electrons have?
Negative.
Very nice. And what charge do the neutrons have? I almost said the charge. Neutrons are
Neutral.
neutral or no charge. Very nice. Great. All right. So we had looked at, I don't know, like 4 or 5 different models of the atom and how it's changed over time and how our thinking has had to adapt, how our understanding has had to adapt as we gain new information. We ended with the plum pudding model where like the whole atom is positive and then you have electrons kind of scattered throughout. We know that that's not true, but we did know from J.J. Thomson's experiments that there is a negative component, the electron, and there is a positive component, the proton, but he was just wrong about how they were kind of spread out in the atom. So this last experiment is called the gold foil experiment, and this was done by Ernest Rutherford in 1911, and he was actually a student of J.J. Thomson's, so he understood positive and negative, that you were going to have those two things, right? And so what he did was he performed an experiment using a super thin piece of gold foil. You guys know like the extra gum that has like the blue and the green foil that you can separate from the backing of the gum wrapper. Okay, so years ago, like people went wild, like putting that foil sticky stuff on the binders and like all over stuff. Did you guys ever do that? There was a group, it was a while ago, but oh my gosh, they would peel that foil from the paper and they would stick that foil on things. And it was super thin. That's what I kind of picture when I think of this gold, right? So it's actually like really thin, flat sheets of gold. So not like a hunk of gold, but like as thin as you can imagine, right? And so it was only like a couple layers thick. And so what they did was they shot radioactive alpha particles that are the non-dangerous or the least dangerous kind, and they hit into this gold foil. Well, gold is an element, and so the element is made of those gold atoms. And so if it's an atom, then it should have that nucleus, and then it should have that empty space around it. So most of the time, when they shot these particles through this gold foil, they just went straight through like you would expect. There was no problem. But a few times, randomly, some of the particles would shoot and like reflect in a different direction that they couldn't explain. They're like, well, what's causing that to happen? And so this led them to the idea that so you have these alpha particles that are positively charged hitting into a positively charged concentration, which we now know is the nucleus. So when the positive hit the positive, we know that those repel. And so it would hit just perfect in one of the gold nuclei, and it would bounce it in a weird direction, here or here. If it missed the nucleus, then it would just go straight through because it didn't hit anything positive to deflect it. And so that's kind of the basic setup of this experiment. Right, so you shot these alpha particles at the thin sheet of gold foil, and I believe that this is a slide that you have to fill in. It's your first one since like slide 10, I think. So right there at the very bottom of page 1. Most of the particles went straight through, right? Like you should see right here. but those special ones were deflected. And so he made that observation, and then it was like, wow, what could be causing that? And he got thinking, well, these are positively charged particles. If it hits something else positively charged, well, it'll reflect it, right? It'll send it away. And that's exactly what happened. We're going to come back to this in just a second. This is going to show the experiment, and people at home watching, there is a video for you. Yes, did I go too fast? Did something happen?
You're no way.
Oh my gosh, just tell me to move. Yes.
Did any of them stick?
You know, I've never heard that. I've wondered that too. I'm not sure if they would know for sure if they would stick or not, because it's not like they're counting. There's one, oh, one weight came through. There's two came through. So I'm not exactly sure. That's a good question. I've wondered the same thing, and I've looked at a couple different sources, and I've never heard that. So I don't want to say yes, they probably did. Chances are that maybe a few did. Like if it's like exactly hit into an electron, maybe like that would attract. Logically, you would kind of think that maybe it would, but most of them were hitting all that empty space. All right. So what was so important about this? Thank you so much for stopping me. What's so important about this is that now we know that the proton, the positive charge, is concentrated in the middle. And now we know that it's mostly empty space that allowed those alpha particles to go through. All right, so that was hugely important to our current understanding of what's going on. So we'll watch those videos at the end. Again, I apologize. You guys, sometimes our videos are going to be a little out of order just because of my taping, but we'll come back to them at the end. All right, so you can kind of see, here's the alpha source, here's our thin gold, and again, most are going through, but a few get reflected. All right, and so that basically sets up our understanding that the atom is mostly empty space, the nucleus is very densely packed, and that the nucleus is positively charged. And that holds true today. That has not changed. So J.J. Thomson set up Ernest Rutherford to kind of be his student, and like he continued his thinking and his work with the atom to get us to this point. So it all kind of evolved, and they built on each other's knowledge to get where we are today. All right. Finally, we have Niels Bohr. He hypothesized that electrons travel in orbits or energy levels around the nucleus. Dylan, I want to tell you, I used your solar system example in all my classes, and I saw some nods like, yeah, like that makes sense. Mm-hmm. So I shared that, and I did give you credit for it, by the way. So yeah, no, thank you. So again, Dylan was saying like this is the sun, and then these kind of look like the planets, all right? So Niels Bohr, and when we're looking at chemistry and looking at energy levels, this is kind of the model we use because it's simple and it's easy to work with. We're going to do something called an electron dot model, and it's kind of based off of his work. It's very visual and very straightforward to see what's going on. It's not completely realistic to what the electrons are actually doing in an atom, but it helps us give us a model that's easy to work with. And so he is responsible for that. And so you can see he called these shells, it can hold 2, then it can hold 8, and then the third shell holds 18. Again, you're going to get into that more when you get into chemistry, but just know that Niels Bohr is the one that kind of came up with that idea. That led to what we know now about electrons, and we call this the electron cloud model, where basically there's not like these set perfect rings, like here's a level, here's a level, here's a level. It's not exactly like those perfect concentric circles, but what's happening is there's areas that they can travel in. They stay within kind of a region, and then like if they get excited, they can go up a level, or if they get unexcited, then they can drop back down to their original level. And so they call these area clouds. Clouds is kind of less rigid and defined as a level or a shell. So it's kind of like these areas that they can exist, but it's not like, okay, you have to be in this track or in this path or orbit. Okay. And again, you'll get into that more in chemistry. if you end up taking that as a junior. So we will listen to this song at the very end again. And it does a good job of kind of putting all this together, and it actually talks about the people that contributed to knowing about the atom. So we have a couple last things we're going to do today before we get to some practice, right? We've gone through quite a bit of notes already in just a day and a little bit. This is one of your vocab terms. This is massively important. You have to know this. You have to keep this atomic number separate from the mass number in your head. You have to find a way to keep them separated. So the atomic number is super important because it's the number that's going to identify the element. This is basically like the fingerprint. So all of us have a unique fingerprint, obviously, that can identify who we are, right? And because of that, we associate the fingerprint with this atomic number because it's going to be what identifies the atom. It's what makes carbon carbon. It's what makes lithium lithium, boron boron. And what it's based off of is the number of protons, and we'll get to that here in just a second. So all atoms of the same element are gonna have the exact same atomic number. So these are typically each element is represented by like a little square, sometimes a little tile. You can see it on the board over there. You can see it on your periodic table. And you're going to have some numbers above this little symbol, and you're going to have a number below this little symbol. This symbol is basically the abbreviation that's associated with the element. So this is helium. H is for hydrogen. C is for carbon. Li is for lithium. A lot of those kind of go together. Potassium is not P, it's K. So not all of them match our word. Some of them kind of go back to their Greek name. Like gold is like AU, I believe, and it's like, what is that, aura, I think, is the name. So yeah, it makes sense based on the Greek word, but not our word for that element. So some of them make sense, and you're like, yep, O for oxygen, I got that one. But then there's some random weird ones too. So you'll get the hang of it. I do not need you to memorize the periodic table. It is there for you to always have a copy of and to look up, so you don't need to memorize it, all right? That's, I think, a waste of brain space. You can always look it up easily, all right? But this is the atomic symbol. Now, the other thing that's a little confusing, sometimes a periodic table will put the atomic number on the top. Sometimes they put the mass number on the top. So you can't just say, oh, the atomic number is the number on top. Some of them will be the number on the bottom. So we have to have another way to distinguish between this number and this number, because they mean different things, and you're going to need to know what those things are. So, the atomic number is based on the number of protons for that element. So every helium atom in the entire universe has 2 protons. If it doesn't have 2 protons, then it's not helium anymore. It's maybe hydrogen, or maybe it bumped up to lithium. It has to have 2 to be helium, okay? So the proton number is what identifies the atom. And so kind of by default, if an atom is neutral and you have 2 protons, which is 2 positive charges, to have a neutral atom, you'd have to have 2 electrons to balance, 1 to balance out each positive proton. So in a neutral atom, the number of protons will equal your number of electrons. But not always is an atom going to be neutral. So we'll get to that here too. Are you lost, Cade? You good?
Yeah, I'm good.
Okay. I couldn't tell if you were trying to get some or not. Okay. So protons are permanent. Changing the number of protons will change the element you have. Protons are permanent. Right? I'll try to exaggerate that. There we go. Protons are permanent. It's like the fingerprint. It identifies the element you're dealing with. All right, now here's another vocab term, the mass number, right? So the mass number is your number of protons plus the number of neutrons. So in this example, here's my atomic symbol, and then generically it's saying that this is the mass number. So this one, it has the mass number, the big number at the top, and it has the atomic number down here at the bottom. I don't know if I have my periodic table up here. Here we go. On your periodic table that you're going to use, the atomic number is at the top, right? But if you look at a different one, like maybe the one that was on that Google form from the other day, the mass number might be at the top and the atomic number might be at the bottom. So you can't memorize the location. You have to think logically, and I'll give you some cheats and some ways to do that to keep those two numbers straight. So the mass number is going to be your number of protons and your number of neutrons. So that hydrogen has one proton and it has one neutron. So that number is 2. The atomic number, 1 proton, so it has an atomic number of 1. All right. Here's how we keep it straight. The atomic number is always going to be the smaller number. Always. Here's how you remember that. Or a way to help. Oh, sorry. Mass number will be the larger one. If you think of an atom and how small it is, it's teensy tiny, just like its number. So the atomic number is small, just like the atom. So if you have a number that's 16 and you have a number that's 8, 8 is going to be the atomic number because it's the small one. 8 is smaller than 16. Then obviously the mass number is going to be the big one. Think of when something is massive. It actually has that word in it, mass, showing that it's the massive one. And again, try not to memorize this stuff. If you think logically, atoms are small. The atomic number is the small one. Mass number, mass sounds like massive, mass means big. Massive means big, right? So it's going to be the big number. So if you can kind of think of those little cheats, it helps because it's easy to confuse these two, and you're definitely going to have to keep the two of them straight. So here's another logical part. The atomic number only counts protons. It only counts one subatomic particle. So counting one of something instead of two of something would always give you the smaller number. And then the reverse is also true for the mass number. You're counting 2 subatomic particles. You're counting all the protons and you're counting all the neutrons. Counting 2 subatomic parts is most definitely logically going to give you the bigger number. So if you're counting just protons compared to protons and neutrons, of course, you guys always are going to say this is going to give you the bigger number. So just try to, this is a very important slide. So like if you want to put a big old star by number 29, that would probably be a great place to start because that's going to be important to help you keep these ideas straight. It gets confusing when you start looking and you're like, which one's the atomic number? Which one's the mass number, right? We always get it, but sometimes this can make it a little easier if you keep this one kind of in check. All right, we're going to stop there.